Okay, this section is about transfer learning. So we are going to discuss some more important things in the transfer learning. So I will let you know what is transfer learning. And then we are going to look more details about fine tuning. And there is a kind of issue when we do the fine tuning. And this is the current method for the fine tuning. We call it the parameter efficient fine tuning. So we will take a look on some of the approaches. Now let's look the definition about transfer learning. What is transfer learning? So based on the definition by Han and Young in 2010, he mentioned that transfer learning, we use the previous experience. So previous experience is used to learn and adapt to new tasks faster and more accurately. So for example, if you learn any programming language before, let's say you learn Java, okay, and you want to learn Python now, because you already have the knowledge about the programming in Java, then you can easily adapt to Python because the structure might be the same, only the language is a little bit different. Maybe the structure is a little bit different, but overall, they are programming languages. For example, if you learn about ping pong, you can play ping pong. Because you know how to play ping pong, then it is not difficult for you to transfer your knowledge to learn tennis. Okay. Because both of them, they use racket and they also use the ball. The only difference is you need to have more power on the tennis, okay, and so on. So with this kind of idea, we can use the transfer learning for the text analytics. So by the definition, what is transfer learning in details? So deep learning shows remarkable success in various fields in artificial intelligence. So if you know about the deep learning, we can use it for the object classification. We can use it for the machine translation and so on. But when we try to create the deep learning, we need to use a very large label data set. So you need to have a good computer to model, to create the model. When you have the good model with this large label data set, there are some questions. How about inferencing new tasks or novel tasks? So inferencing, it means how we can check the new task, how we can check the novel task, the task that has not been available before. What if we do not have labeled on testing dataset? So we have the training dataset and we have the testing dataset. Now you have only the testing data, but you don't have any label. Meanwhile, your training dataset has a very huge label. Or what if the data, or we call it the target, is different from the training set? For example, we call it as the source. So let's say, I mentioned to you like ping pong. So you can play ping pong. And I want to transfer to tennis. So we call it, this is the source. The source data that you have is about playing ping pong. But you want to recognize and you want to learn about tennis, which is the target. So if the target is totally different from the training set or the source, then we need to do the transfer learning. So we need to transfer some of the knowledge. So we call it transfer learning. The transfer learning aims to extract. So we need to extract the knowledge from one or more source tasks. So we call it source. It means we have the sources for getting the knowledge and applies the knowledge to a target task. So there should be a target that we want to use. In the traditional machine learning, so you can see we have the task 1. So this is the data, and then we do this learning system. We have task 2. So we do the machine learning, and then we got the model. We have task 3. We learn from the data, and then we got the model. So the task will be different because we have different data set. But now, if you use the transfer learning, so you can just collect, okay, this is the task 1 data, this is the task 2 data. You can pull all those data into the source, and then we can learn this data. After we extract the knowledge, we can use this knowledge to understand this target task. Then we can have a model, and this model will be used to predict this target task. Why transfer learning in NLP? So the NLP is the text analytics that we learned until now. So many NLP tasks share common knowledge about language. So we have the common knowledge. It means if you learn about the language, we have the linguistic representation. The linguistic representation means every sentences we have the subject, 주어, and then we have the verb, 동사, and we have object, 목적어. So if every linguistic have this kind of representation, then we can try to discover the common knowledge between the language. The structural similarities. Maybe if you want to translate from Korean to English, it is complicated because the structure is different. But when you try to translate from Korean to Japanese, maybe it is easier because the structure is similar. So we have the structural similarities. So we need to find what is the common knowledge between the language or between the representation and extra. So tasks can inform each other. For example, the syntax or maybe the semantics. And also the annotated data is rare. Annotated data means the label data. When you have a new data, for example, I think in your project, some of you have difficulties to have this label data. You got the data from neighbor. You got the data from some news. You got the data from the media portal, but you don't have any label data. Then you need to have the supervision, and it is also difficult. We can leverage the transfer learning for this issue. So empirically, transfer learning has resulted in state-of-the-art, or we call it SOTA, for many supervised NLP tasks. Okay. So the transfer learning has been proof that is useful for classification, maybe for the sentiment analysis, for the task classification. It is also useful for the information extraction. It is useful for the Q&A, like the chatbot and etc. Yeah, if we look at the structure in the transfer learning, we have the same task, but the label data only in the source domain. What does it mean? Let's say I have the data. So the data, maybe I have the data about news. So the news that I use is from a media in Korea. And then now I want to do the sentiment analysis. Meanwhile, I have also news, which is the media in US. And maybe the news is related to Korea, but the language is in English. And I want to do the sentiment analysis. So we call this is the sentiment analysis is task. We have the same task. We want to do the sentiment analysis, but the label data only available in the source domain. So I have the label only in the media in Korea, but I'm not sure what is the label in the media in US. Then you can use this method. For example, we have the transductive transfer learning. So if it is in the different domains, we can use domain adaptation. If we use different language, we can use the cross-lingual learning. Okay. Different domain. Maybe if we know about in Korea, there are many news portal. So let's say you are using the Naver news. So use the Naver news to get any information about sports. But in US, you use the maybe CNN for sports. So you know that Naver actually it is not a sport media. So they just collect all the media and they just put on that portal. Meanwhile, CNN is a news portal. So they have different domain. Then we can do the domain adaptation. If it is different language, then we use the cross-lingual learning. Then if it is different domain and if it is different language, we can use both of them. The other kind of transfer learning, we have different tasks and label data in the target domain. So we can use the inductive transfer learning. There is a word about multitask learning, or we can also use the sequential transfer learning. For example, if you have the different tasks, you already did the sentiment analysis. Okay, so you have the model. And now you want to use this model, not for the sentiment analysis, but you just want for the media classification. So this is different task because the first task is about sentiment analysis. The result can be positive or negative, but the media classification, maybe you have the task result is whether it is about economy or not economy. So using these kind of things, we can leverage the transfer learning, and we can use the multitask learning, or we can use the sequential transfer learning. Okay, there are some definition about the transfer learning from the research from this researcher Pan et al. In 2010. He make a kind of definition about domain and task. So domain means we have a feature X and we have a marginal distribution Px over the feature space. So X is the data that we have, and then Px is the marginal distribution, or it is a kind of representation from this data. And then the task is we have the label. For example, this is Y. This represents the label space. And we have the conditional distribution. So what is the probability of Y given that the data is X? So in the transfer learning means we have the source domain, DS, and learning task, TS. So DS, we have D, we can have DS, it is about the domain from the source. And we have DT, which is domain for the target. And then T, we have TS, it is the learning task in the source domain. And we have the TT, which is the learning task in the target. So transfer learning aims to improve the learning of the target predictive function, which is FT, using the knowledge in DS and TS. So we want to use the DS and TS to recognize the data in the DT, and we want to predict the TT or the target in the T. So this one is the condition. The domain of the source is not equal to the domain of the target, and the task of the source is not the same with the task in the target. So let's see more detail about this one. When you deal with the transfer learning, so as I mentioned before, the DS or the domain of the source is not equal to the domain of the target, or the task of the source is not equal with the task on the target. Now let's see. If the task is equal, so the task of the source equals to the task of the target. If it is yes, then let's check. If the domain of the source equals to the domain on the task, so on the target. If it is yes, okay, you can just apply the traditional machine learning. In some cases, you can use the knowledge distillation. You can use semi-supervised learning. So if your data has no label, or the label is only limited, then you can apply the knowledge distillation or the semi-supervised learning. But if the task is the same and the domain is not the same, then you can use the transductive transfer learning. We call we can use domain adaptation, because in this case, the domain of the source is not equal to the domain of the target. What about the task itself? If the task of the source and the target is the same, we can go to this section. But what about if the task of the source is not equal to the task in the target? So we will check whether the Y, the label on the source or the label on the target are observable. So we say that whether the label exists or not. If the label exists, then we can use the inductive transfer learning. So there are some tasks like what we saw before. We can have multitask learning. We can do the continual learning. But if there is no label, if the data has no label or unlabeled, then we can apply the unsupervised transfer learning. So as I mentioned to you, the task, the same task. The task means something related to the task that you already learned until now. For example, we can do the text classification. This is the task. Or text summarization. Or maybe we can do the topic modeling. Or we can do the question and answer modeling, and so on. So this is the task. If the task is the same, then you can split this. So the domain means, let's say, I use the data on the tennis. So the domain is I have the data on the tennis, and then I want to transfer also on the data related to the tennis. Then the domain is the same. But if I have the data on the ping pong, and I want to recognize the data on the tennis, then the domain is not the same. Then we do this one. Okay, that's the meaning by the domain and the task. So the same task and the same domain. So let's see more detail. When tasks and domains are the same, usually one can transfer knowledge for making the target model that are smaller, or maybe we call this is the model compression. So if you know already the pre-trained model, now you know the LLM or the BERT or any other pre-trained model, they are very big. So now the parameter you can get until 17 trillion parameters. So it is so big, you cannot use directly in your computer. So we can compress. We call this is model compression. The big model, we can compress it maybe until the LLM, we call it the SLLM, small of the large language model. Maybe we want to get only 1 million parameter. Okay. Then we can use this one for predicting the task in our computer. This we call it, it performs better than the scratch learning. What does it mean by scratch learning? Scratch learning means you just make the model from your data. Okay. So in your project, when you meet me and discuss your project with me, some of you already collect the data. Maybe you have 5,000 data. With the 5,000 data, you want to create the sentiment analysis. Is it enough to create a good sentiment analysis on the text analytics? 5,000 data is very small. So usually we have like 1 million data, or for the LLM, they use billion or trillion data. So you can use the model compression. After you compress the model from the LLM, you can use it for your modeling. So if you do with the scratch learning, it means from your 5,000 data, you do your classification. Okay? You do your own classification, and then you try to do the sentiment analysis. Is it working? Yes, it is working. But the performance will be low because your data is small. So we call this is the use of knowledge transfer from the source model. If you have very big data, so we transfer the model into this small data. There is a concept about knowledge distillation. So we will learn about this knowledge distillation. We are making a target model mimic the source model. So the target model and the source model, we want to mimic, or we want to make it similar. So make the output or the features similar. Since the task and the domains are the same, so following a resource or reference model is useful. For example, we have the domain of the source is equal to the domain of the target. We have a set of images. This is, let's say, the domain of the source. And we have another set of images. This is the domain of the target. And then we have the task, which is person recognition. I want to know who is the person. And for the target, I also want to know who is the person. So let's say this data set has a big data, or we have a lot of resources. So we can just transfer, or we can just distill the knowledge. We call it knowledge distillation. We can adapt this data into this task. So the other kind of transfer learning, we call it transductive transfer learning. The task is the same, but it is different domain. It labels to predict are the same, but the input data samples are different. Since the tasks are the same, by learning the features invariant to source and the target domain, a target model can perform well. So we call this is feature invariant. Feature invariant means I have the features where is the source and the target. They have the feature 1, for example. They have the features 2. And we want to look at the specific features. What are the specific features between the source and target? So if I try to transfer the knowledge from F1 to F2, it becomes equal or similar. In many cases, the target domain dataset do not have sufficient labels. So the target domain means we have the DS, we have the DT. So the target domain, they don't have sufficient labels. So the Y on the target, usually they have very limited label. So by learning domain invariant features, source model representation could be used for the target domain. So if we have the model from the source, we can use the model to predict what will be the Y in the target. So let's see, this one is an example. We are not doing this part, but if you look at the data, if you look at this data, this is a digit. digit classification. I want to know whether this is a number. Yeah, you can see from here, okay, this is 6, this is 2, this is 3, 8, 1, and 0. Okay. So this is from a source, we call it DS. The data here is totally different with this data. So this is another domain, or this is another data set. We call it DT, domain T, or the target. Now, we want to learn the representation from this data. We know that this is a digit classification. We can get the features. And after we have the model, we want to transfer this model to recognize the digit in this data. So we call this is the domain adaptation. Learn the representation that confuse source and target domain inputs. And learn the target representation that are similar to the source domain. The other kind of transfer learning, as we already learned the classification, it is different tasks. If they are different on the tasks, or we can use the inductive or the unsupervised transfer learning. So the different tasks means we have different labels to predict. When tasks are different, feature extractors and output layers are needed to be adjusted a lot for this new task. We can use the multitask learning or fine-tuning. It is to learn the appropriate representation for the target task from the source model representation. So there are some, maybe I can say, crazy researchers because they try to do the recognition with totally different tasks. For example, this is the person recognition. This is the data about picture, but they want to recognize about the scene classification. So the domain is totally different. The domain of the source and the domain of the target is totally different, and they want to recognize this one. So there's also a research like that. But maybe if you look at this, you can see, for example, now I have this data. I want to look at the scene classification. And I want to look at the task object classification. So the scene is about elevator, the gas station, or maybe this is castle or cafeteria or cabin. And the other task is about the object classification. So I want to know whether it is a car or it is airplane, it is a panda, lion, guitar, and etc. So the task is different. Task is different. And the domain is also different. Yeah, if you put this domain into this domain, which is totally different, of course, this is very difficult task, or this is very challenging task. But we can try with something specific. For example, using this picture, I want to recognize the age. Okay, this person, maybe he is 31. This person, maybe he is 49. This person, maybe he is 34. But the other task here is the person recognition. So I want to recognize who is this guy. Okay, he is John. Who is this guy? Okay, he is Aaron. Who is this guy? Okay, maybe he is Adam, and so on. So the task is different. The domain is the same. Okay, so we can use this inductive or the unsupervised transfer learning. In the transfer learning, because we call it transfer, so we need to move or we need to shift some parts from the model from the source into the target. The fine tuning means we have a source model. Let's assume that the model is already pre-trained. So last week we learned about the pre-trained model, and we have a large data set. For example, BERT. So BERT is already well generalized. You can use BERT in many kind of text classification or word prediction. And one can expect it as a good feature extractor or parameter initialization. So when we use BERT, last week we learned that we can use the tokenizer, BERT tokenizer. When we use the BERT tokenizer means we want to make the word that I have, and we want to tokenize with some values from BERT. Because we know that BERT is already a reliable model. However, we need to concern with the overfitting. One can often freeze layers for the small target dataset. Okay. So we have the big dataset. When we training on the big data, once we transfer it, so we need to freeze some layers because the data is too big here, and when there are many layers, it is good. But when we have a small data set, if we include all the layers, it is not good. So we need to freeze the layers. So we can transfer to different domain and tasks. So if we have different domain on the small data set, if we have different tasks on the small data set, we can transfer it, and at the end, we can fine tune it. So in this case, if we are dealing with the full fine tuning, we need to look at the architecture. So if the same architecture applies, okay, then we can apply the full fine tuning. We can apply this full fine tuning, at least for the feature extraction part. So this is the feature extraction part before we do the classification. Because this is a full fine tuning with this kind of assumption. The assumption for fine tuning approach is the features or the parameters learned from some tasks are useful for another task. So if I have the picture recognition, okay, or person recognition. In the person recognition, we can check the eye. Okay, we can check the nose. We can check the mouth, and etc. So we know that there are some features. There are some features. If the source pictures have those kind of features, and if we are doing the target prediction with similar features, okay, we can do the fine tuning, okay, because we know that there are some features that can be used for the task or the parameters. So the parameters, we have different parameters for every model. It depends on the model. Let's say if you have the layer, okay. If the layer you use the 1D CNN, okay, the source we use the 1D CNN, and the target we can also apply the 1D CNN. Then some parameters here we can transfer it to this model. So we call this is the features or parameters learned from some tasks are useful for another task. So this is true in many artificial intelligence tasks. For example, if we want to have the low level features of text, such as ads. Ads means maybe in the application in your email. So this is what we call sometimes as the ads. When do they fail to work? So when the data set of source and target tasks are very different. So as I mentioned to you, maybe the source data is about person, but the target data is picture about scenery. So if the data set is totally different, of course, it is not working well. And when the target tasks have no label training data, so if the task different, the task on the source is not equal to the task on the target, and the target has no or very small label training data. So sometimes the full fine tuning is not working well. Okay, I think I will stop here. So because when I explain this one, there will be examples that I need to explain as well. Okay, I will stop.